Today, we're diving into rates of reaction, what they are, why they matter, and how we measure them. Understanding how fast reactions happen helps us control everything from cooking to industrial processes. Let's explore the factors that speed things up or slow them down, and see the science behind the pace of change. Let's talk about what affects how fast a reaction happens. The rate depends on several things, like how much of the reactants you have, their temperature, or even how small their particles are. Pick one of these factors and explain it fully. For example, if you choose temperature, you could describe how heating reactants makes particles move faster, leading to more collisions and a quicker reaction. You can use words or drawings to make your point clear. Let's talk about how particle size affects the speed of a reaction. When the particles of a reactant get smaller, the reaction happens faster. Why? Because smaller particles mean more surface area is exposed. More surface area means more chances for particles to collide and react. So the smaller the particles, the quicker the reaction. Of course, reaction rates depend on many conditions, but particle size is a key factor that changes how often particles bump into each other. Let's talk about how temperature affects the speed of a reaction. When we raise the temperature, the particles in the reactant start moving faster. That means they collide more often and with greater energy. Because of this, the reaction speeds up. In fact, the rate roughly doubles for every 10 degrees Celsius increase. On the flip side, cooler temperatures slow things down. Now, adding a catalyst is another way to speed things up. Catalysts create an easier path for the reaction, letting particles collide successfully with less energy. Biological catalysts, by the way, are called enzymes. Let's look at how different conditions affect the rate of processes we see every day. First, plants grow faster inside a greenhouse than outside because the environment is controlled. Warmer temperatures and higher humidity speed up growth. Next, potatoes cut in half cook faster than whole potatoes since heat penetrates more quickly through the smaller pieces. And finally, food lasts longer in the fridge because cooler temperatures slow down the chemical reactions that cause spoilage. These examples show how rate changes with conditions. Let's look at how rate changes with different conditions. When we cut potatoes into smaller pieces, their surface area grows, and that speeds up cooking. Inside a greenhouse, the warmer temperature boosts plant growth, making them grow faster than outside. Meanwhile, cooler temperatures in a fridge slow down decomposition, keeping food fresh longer. So smaller size means faster cooking, warmth means faster growth, and cold means slower decay. These examples show how temperature and surface area directly affect the rate of processes around us. Let's break down how we'd approach this experiment. First, we need to figure out how to determine the rate of reaction. What measurements or observations tell us how fast things are happening? Then, imagine changing the amount of magnesium powder to 1 gram. How might that affect the rate? Finally, think about what would happen if we raise the temperature to 600 degrees Celsius. Each change helps us understand the factors that influence reaction speed. Let's look at how we'd measure the rate of this reaction. One way is to record the mass of the reactant mixture over time, then calculate how quickly that mass changes. Now, if we used 1 gram of magnesium powder instead, the rate would increase. That's because smaller particles mean more surface area for the reaction to happen on. And if we raised the temperature to 600 degrees Celsius, the reaction would speed up even more, you'd see more fizzing, and it would finish faster. Let's take a closer look at how the reaction rate changes over time. We're asked to calculate the average rate between different intervals, from 0 to 10 seconds, 10 to 30, 40 to 60, and 0 to 50 seconds. The table shows how much gas is produced as time passes, and by comparing these intervals, we can see how fast the reaction is going at different stages. This helps us understand what's speeding up or slowing down the process. Let's look at how to calculate the average rate of a reaction over different time intervals. We find the change in volume of gas produced, then divide by the time elapsed. For example, between 0 and 10 seconds, the rate is 2.5 cubic centimeters per second. As time goes on, the rate changes, usually slowing down. That's because the reactants get used up, so the reaction has less fuel to keep going fast. This slide shows those calculations clearly. Now we're looking at how temperature affects the reaction time, specifically, how long it takes to collect 40 cubic centimeters of gas. First, we calculate the rate of reaction for each experiment, measured in cubic centimeters per second. Then, we explore the connection between temperature and reaction speed. As temperature changes, the time to collect that gas volume shifts, and understanding this relationship helps us see how heat influences reaction rates. Let's look at how temperature affects the speed of a reaction. As the temperature goes up, the time it takes to collect a set amount of gas goes down. They're inversely related. First, we calculate the rate of reaction by dividing the volume of gas collected by the time taken. Then, we see that higher temperatures mean faster reactions because the molecules move more quickly and collide more often. This slide helps us connect temperature directly to reaction speed. Here, we're looking at how to analyze the data from a gas production experiment. First, we need to calculate the average rate of reaction during the first 20 seconds. That gives us a sense of how fast things are happening early on. Then, we identify the time when the reaction stops and state the total volume of gas produced. Finally, we imagine how the graph would change if we repeated the experiment at lower and higher temperatures, adding curves to show those expected results. This helps us understand temperature's impact on the reaction. Here, we're looking at the results from an experiment measuring gas volume over time. The graph shows how the gas produced changes as the reaction progresses. We're asked to think about how this graph would shift if the experiment ran at different temperatures, lower or higher. We also review key details. The reaction stops at 60 minutes, the total gas produced is 60 cubic centimeters, and the average reaction rate in the first 20 seconds is 2 cubic centimeters per minute. Let's look at how we calculate the rate of reaction using this example. We have a freshwater fish tank and a test kit that measures ammonia levels. The tank owner tested the water before and after adding a chemical that reacts with the ammonia. The reaction took 37.5 seconds, and the test strip changed color from green to light yellow. Using this information, we can determine the rate at which the reaction occurred, a key step in understanding how quickly the chemical affects the tank's environment. Let's work through calculating the rate of this reaction. We know the change in quantity, that's 0.75, and the reaction took 37.5 seconds. The test strip's color shifted from green to light yellow, showing the ammonia levels changed. Using these details, we can find the average rate by dividing the change in quantity by the time taken. It's a straightforward way to see how fast the reaction happened in the tank. Let's look at how the reaction progresses over time. First, we want to calculate the average rate of reaction between 0 and 4 minutes. This gives us a sense of how quickly the reactants are changing in that early phase. Next, we need to identify the exact time when the reaction stops, marking the point where no further change occurs. Finally, we'll consider why the reaction stops, what factors cause it to come to a halt. This helps us understand the full picture behind the data on the graph. Let's look at how we calculate the average rate of this reaction between 0 and 4 minutes. We start by finding the change in quantity. Here, it's 160 minus 148 grams per minute, which gives us 3 grams per minute. Then, we divide that by the change in time, which is 4 minutes. The reaction stops around 8 minutes because the reactants are used up. There's nothing left to keep it going. This slide wraps up those key points with the answers. Here, we're looking at how to calculate the average rate of change. It's the difference in quantity divided by the difference in time, basically, how much something changes over a certain period. On this slide, you'll complete the data in the table by rearranging the formula. This helps us understand the pace at which things happen, whether it's speed, growth, or any other rate. Let's make sure we get the numbers right. Here, we're looking at how to calculate the average rate of change. That's the change in quantity divided by the change in time. The numbers in the table represent different values we'll use to find that rate. Our goal is to rearrange the data correctly to complete the table and understand how the quantity changes over time. This step is key to making sense of the overall trend in the data. So, how would a chemist figure out the rate of this reaction? Here, acidified potassium permanganate reacts with oxalic acid, producing manganese ions, carbon dioxide, and water. The key is to track changes over time, maybe by measuring how quickly the purple permanganate fades or how fast carbon dioxide bubbles form. By monitoring these changes, the chemist can calculate the reaction rate and understand how fast the process is happening under given conditions. So how can a chemist figure out the rate of a reaction? Well, they track changes over time like shifts in mass, volume, or pH in this case. Measuring the volume of carbon dioxide gas produced gives a clear picture of progress. Using specific equipment, they can collect and measure that gas accurately. With this data, they draw graphs to analyze key points, like when the reaction ends, how much product forms, and how conditions affect the rate. From there, calculating the average reaction rate becomes straightforward. This video was created with SlideSpeak. Visit SlideSpeak to turn your presentations into engaging AI-narrated videos.